First of all, thanks to everyone for being here today, attending this lecture. We're going to talk about a topical subject, which is how we can assess the factual accuracy of large language models. And perhaps my first important slide is this one, which is this is really joint work with John Chirian and Isaac Gibbs. Isaac used to be a PhD student at Stanford and is now at Berkeley, and John Chirian is at Stanford. And I think I'm really the messenger here. Most of the heavy lifting, if not all of the heavy lifting, was done by John and Isaac. By the way, I should say that they are on this call, and so they'll be ready to answer any question you may have during this lecture, either through the chat or after the lecture is over. So I don't think I need to tell you much about LLMs. We use them all the time to streamline our work and be more efficient. Let me just close my door just a second. So sorry about that. So we asked ChatGPT to actually write a detailed and concise biography of Nikolaus Bernoulli. This is one of the members of the Bernoulli Brotherhood. And then ChatGPT is very happy to oblige, and it's writing a short biography. And, I don't know how many of you are familiar with Nikolaus Bernoulli, but some of what is being claimed is actually correct, and some of it is not. And I think we've all experienced interacting with these chatbots where we get what sounds like to be a very authoritative answer to a simple query, but we're not supposed to trust the entire thing. So you get a list of a paragraph of this kind, and what you're going to do is we're going to use the language model itself to actually parse this text into a series of self-contained claims. And so from the paragraphs we've seen before, we can see that there's a claim that Nicolas Bernoulli was born in 1695, that he died in 1726 at a fairly young age, that his work continues to influence people to this day, and so on. And the thing is, sort of, should we keep these claims or not? Are they factually correct or not? So if you look at the literature, mostly in computer science these days on chatbots and hallucinations and claiming and scoring claims, you see thousands and thousands of papers. And one way you can try to understand whether a claim has a chance of being correct, there are many ways of doing this. First of all, you can ask the language itself about how certain it is that the claim that they just made is correct. Or you can, for example, here is another way of doing this is you can ask the chatbot to actually produce many biographies. You can repeat the query several times. And if a claim is made many, many times, there's perhaps a higher likelihood that the claim is correct versus not. So here, for example, when we query ChatGPT, we see that the date of birth and death are actually changing. So perhaps we're not so sure about these dates. So as I said, it's a topic of considerable interest, not only in the area of language models, but in other areas of AI. As we use AI systems to automate tasks, how do we know that the AI system has done it correctly? Is it possible to score the AI system on various tasks? And so people develop claim scores, and we want to use the claim scores to actually filter the claims. And what this talk will discuss mostly is how we can take claim scores. We'll see how we can improve them a little bit, but we're mostly going to take them as given. And how should we process these claim scores to actually come up with a list of filtered claims so that what you're actually presenting to the user has a reasonable chance of being correct. So this is the subject of this talk. And I'm going to tell you of a paper that is very recent, actually. It's from earlier this year, I think about around February, March, of two computer scientists at Stanford University, Mori and Hashimoto. And here is the method they proposed. This is a simplification of what they proposed, but really it has all the essential components. So what you're going to do is you're going to obtain ground truth annotations for a set of exchangeable prompt output. And so, for example, you make a claim, you have your score to kind of a high score indicates that the system thinks that the claim has a chance of being correct. A low score means that maybe it is not. And then for each claim, you have actually a person annotating the claim, whether it's correct or not. So for example, if we were to actually run this on Leonard Euler, we would have a claim that Euler was born in Basel, Switzerland, and maybe, the system would give a score of 3.7, and then a person would actually check this and see that it's true. We would have his date of birth. The score might be a bit lower in this case, and it turns out that it's false. He was not born in 1708, that he was a mathematician. That's a true claim. And then you can do the same for different mathematicians, statisticians, and so on. And so you are actually creating a data set where you have on one hand a predictor variable, which is your score, and on the right, the true label, the status of the claim. So you obtain ground truth annotations for data sets such as this. And then you're going to compute a threshold. This is what, for people familiar with conformal prediction, we're going to think of a conformity score. But at this level in this lecture, it's not really necessary to understand conformal prediction. We're going to compute a threshold at which all claims are filtered. All false claims are fictional. So for Euler, the threshold would be 1.6, meaning that all the claims that have a score higher than 1.6 are actually true. And for Euclid, that threshold would be 2.3. So this is a score, a conformity score, as we'll see in a minute, at which all false claims are filtered. And then we're going to look at all these people for whom we want biographies, representative people of the type of biographies we'd be thinking here. We're looking at the mass stats community. And so you see my colleague Brad Efron, and he has his threshold, and Definity has a threshold, and everybody has a threshold. And I would like to understand what threshold should I apply to Bernoulli, since I don't have a ground truth annotation for that person. So what Mori and Hashimoto propose doing is I'm going to look at all the scores, the thresholds for which I have the calibration data. I'm going to compute the 90th percentile. Let's say it's 4.1. And what I'm going to do is I'm going to filter all claims such that I'm only going to keep those which score exceeds 4.1. Okay. Now, when I do something like that on so this is essentially the method that these two computer scientists proposed. When I do something like this, it gives you, we'll see later on, that it gives you a formal guarantee that actually with probably 90%, what survives the thresholding operation is actually, all of it is true. But the problem here is that it removes everything, right? The system has no confidence that you can actually print anything. And so even though, as we'll see in a minute, we get a super cool guarantee about the likelihood of what you see being true is high, it's 90%, the problem is that there's nothing that survives this thresholding operation. So there are challenges with this. It's a good first step in the right direction, but it might not be useful because the utility of such a system, as you can see, is somewhat limited. So first of all, is it okay to just have a marginal threshold estimation, not paying attention to whether you're a statistician, a mathematician, a topologist, and so on? Are we using a scoring function which is not powerful enough that it cannot really discriminate whether a claim has a chance of being true or not? And asking that we're 90% correct in everything we say, is it too optimistic? So we're going to revisit this, and we're going to propose an alternative to this way of filtering out claims that achieves different goals. First of all, one thing, because we want to preserve the utility of the output, that we're going to insist on is that we want to retain as many claims as possible. So for this lecture, we're going to focus on one attribute, which is that we want to retain 70% of more of the claims that are produced by our language model. If I retain a lot of claims, I may not be able to say that what you're seeing is true with high probability. So what I need to do now is I need to change the rule of the game and to provide a calibrated assessment of the chance of being correct. And we're going to ask a bit more, because claims and the way you interact with a chatbot, and we'll make examples later on, there are different types of prompts, there are, different areas of knowledge that you want to probe. It would be very bad for us to to be very accurate on a subset of prompts and very inaccurate on another one. So we would like also, if we keep on thinking about writing essays about individual, that this correctness that we're going to give you, this chance of being correct that we give you, be valid conditioning on whether you ask to write a biography of a male or female, someone living in the United States or not, someone alive or dead, and so on. So we want more guarantees that of correctness. And so when we apply this system, which we'll spend a lecture detailing, to the prompt, so the output of ChatGPT on the Bernoulli, we get that we're going to remove some claims. And so the system will filter out claims, but it will leave some. And so everything that is being struck through has been removed by our system. Everything that you see in bold is actually wrong. It is not true that Nicholas Bernoulli worked on the St. Petersburg paradox. So we actually removed this claim correctly. And what the system will tell you is that with probability 36%, everything that you see that has survived the filtering is actually true. So now I use a bit the word probability, and we have to understand what it means when I say probability. I mean this in an empirical sense. That is, each time our system says, and we're going to make this formal in a minute, but each time the system says this claim has a 36% of being true, I could look at all the times where I say your 36% chance of being correct, then it will be actually 36%. Right? So not 45, not 25, 36%. That's what we mean by calibrated. Okay, so in this case, actually, the system evaluates that the chance that what we see is true is 36%, when in fact, everything is true. So just to show you a little bit about what it would produce on a medical data set that we'll discuss a bit later. So we have several types of medical questions we could ask to a chatbot, and these are indicated by the categories that we see on the right. And so what we can see on this plot is we can see two things. One is that when I announce the probability, the nominal level, let's say I announce that my claim is true, is what you're seeing is true is chance 70%. What we can see empirically, if you see my hand, is that it's actually true 70% of the time. So that's a sense in which our system is well calibrated. When we announce 70%, it is 70%. What we can see on the right chart is we're going beyond calibration by actually trying to, the orange box plots show you the number of claims you can retain in this medical data set per category if you want a 90% chance of being correct. And so what you're saying is that you're going to, if we look at the health search Q&A, that we're going to remove a lot of claims. We're going to only keep 40% of the claims. By being a bit more adaptive, we can keep many more claims. Now the confidence at which we say things is not 90% anymore. It's going to be adaptive, but it's going to be well calibrated, as you can see on the left. And I hope this plot makes sense, because it really summarizes a lot of the output that we're going to provide users. This is the same thing on the biography. So this is showing you that if we are becoming adaptive, we can retain the 70% of the claim, and sometimes more than 70%. Here we grouped biographies in different groups, whether they are, these are biographies of individual, let's say on Wikipedia, that are frequently accessed versus not. So I guess I might be in the rare or very rare category, and Abraham Lincoln would be in the very frequent category. And so you can see that the portion of claims we return depends on the category you belong to. We see again that we're extremely well calibrated, and we see that if you wanted 90% accuracy, as we've seen before, you would not be able to say very much about any individual. Okay, so I think what we want to do in this remaining lecture is to explain how we get these results, and hopefully you'll see the interaction between a system that hopefully does something useful, and statistical thinking. So our methods have several key components. We're going to discuss them in turn. First, we're going to partition the data set to understand at which level I should make a claim about an individual. And then how should I boost, if you allow me to say so, the scores that I'm going to get to assess the accuracy of a claim to retain as many claims as possible. Right? So we're going to do this on the first split of the data set, and then we're going to calibrate on the second split of the data set to output a set of filtered claims. So we're going to we have three boxes: adaptive level estimation, how we optimize the scoring of the claims, and the conformal calibration, and we're going to discuss all of them. So we're going to start with conformal calibration. And I don't know how many people in this room are familiar with conformal prediction. It's a very hot topic in statistics and machine learning at the moment. We're not going to really discuss conformal prediction. We're going to see how it applies to our problem. So it turns out that the method I presented before is a very straightforward example of split conformal. So I'm going to abbreviate this with by CP in the rest of the talk. So it's an abbreviation of split conformal. And so the mathematical setup, if you will, is that you're going to have n+1 prompt claim annotation tuples. So there's a bit of notation, but we cannot keep them very long. So PI is your prompt. CI are the list of claims that the chatbot will produce after you write the prompt PI. And AI will be a list of binary variables indicating whether each of these claims is true or not. Of course, I'm writing a new essay about an individual. This is what I'm going to call the test point. This is a point n+1, which is not in my training set. So I do not know the status of the claim Cn+1. So An+1 is not observed. Sorry, I'm going in the wrong direction. An+1 is not observed. So we have, for each of these claims, we have a score, which I mentioned before, a score function. There's, as I mentioned, there are thousands and thousands of papers explaining us how we should try to score claims. So we're not going to really discuss this in this lecture. We're going to take this as a given, which evaluates a high score means probably a claim has a high chance of being true. And so I'm going to calculate what you've seen on the previous slide for the ICE data point for which I have annotation. I'm going to look at the largest claim score above which all the smallest claims score above which all of the claims are true. Right? So this is exactly what we calculated before. If the score is 2.3, if SI is 2.3, it means that for prompt I and claim CI, every claim above that has a score above 2.3 is actually correct. And then we're going to filter the claims. We're going to keep the claims whose scores are above a threshold tau. What this says, if we follow a little bit our notation, is that if tau is above the conformity score SI, then what I'm producing is actually entirely factual. Is that clear? Okay, good. So the question is, how do you choose tau? And what we're going to do is that's where we're going to use the ideas from conformal prediction. We're going to use tau using a high probability. We do not observe Sn+1 because we do not know the status of the claim for the test point. So we're going to use a likely upper bound on Sn+1. So the say is that suppose Sn+1 is S20, we have the conformity scores, the thresholds that we calculated. They are here. They are what we can calibrate, what we can compute on our calibration set. And we ask, where will S20 go? And because I'm sort of randomly sampling claims IID from a prompts IID from a population of possible prompts, well, there's nothing really that distinguishes a test point from the calibration point. And so it's equally likely to be of any rank on this axis. In particular, if I choose a score to be the 90% of the scores I've seen on the calibration set, then S20 has a 90% chance to be below this quantile. And by virtue of what we've seen before, it means that if I were to choose this threshold, I would actually produce stuff that are correct 90% of the time. And what you're seeing here is you're seeing conformal prediction in action applied to factual correct guarantees for a language model, but this, of course, strategy is far more general than this. So what we're saying is the test point is let's write a biography for Bernoulli is exchangeable with the calibration point, the point on which I train my system. And therefore, we use this exchangeability to say that if we were to actually choose the threshold with a quantile that we saw on the calibration set with 90% probability, S20 will be below that quantile, and therefore what we print will be correct 90% of the time. So this is conformal prediction, but as you've seen, it removes pretty much everything, so it's not exactly useful. Another problem we have with this method is that, and that's something that people often criticize about conformal prediction, is that it's only marginally valid. So what I mean by that is it's average over the next prompt. And the problem is the next prompt might be about different areas of medicine. Think about my example where I asked the chatbot a medical question. And what would be a bit unfortunate is to have very different levels of accuracy depending on the kind of questions you ask. And so that would be really unfortunate. So we would like to have guarantees that are more conditional, right? So if I ask a question in emergency medicine, I would not like to have, to know that the thing is actually correct 90% of the time. Marginally is useful up to a point, because if it's never correct for emergency medicine, that's not something that is really good. So we would like to have, and that's often a very sharp criticism of conformal prediction. It's only valid marginally, but not conditionally on attributes here of a claim, of a prompt. It might also be the case that if we were to look at our proposal on different areas of medicine, to retain a 90% guarantee, I'm going to have to filter out so much stuff in areas of medicine that the thing becomes absolutely useless. So we're going to need to address this. So what would we want? We want the method to be distribution free. I mean, I have no power to actually model this LLMs parametrically or anything like this parametrically. We want to be able to use whatever people in engineering and tech companies are using. We want to use a complex black box scoring model. And typically what we would want is we would want that what the system produce, conditioned on the prompt, has the advertised probability of being correct. Right? So there are attributes of the prompt. For example, is the prompt very long? Is it about a sensitive topic? Is it about a toxic topic? Is it about the election? I would like to have a guarantee that is conditionally valid on attributes of the prompt. The thing is, if you go too far in this direction, there's a famous result in conformal prediction that says that you can't do that. If that's the guarantees you want, the conditional guarantees you want, then what you have to be returned has to be empty with high probability. There's nothing you can say, so it's not useful. I see that I have a question, so I think it's probably a good idea for me to pause for a little bit and take one question, perhaps along with John and Isaac. Please.
Thank you, Candès. Yiming, please, I saw you raise your hand. Please go ahead and talk. She lowered her hand. So
Okay,
I
so
think yeah, we
I'm going to continue. I'm very happy to pause and entertain questions. I'm going to continue, but if a question comes up, I'm very happy to pause. Okay. So what conditional validity means, it means that the output has to be factual, conditioned on the prompt. And that's what conditional validity means by definition. Marginal validity says no. I mean, you average over all possible prompts. And so what you just need to guarantee is that, to suppose alpha of P is just, I don't know, the error rate of, say 10%. It means that the probability, no matter the claim, on average, that you're correct is 90%. So to explain a bit the ideas we're going to present is we can think a little bit about, we should think about conditional validity as this, which is that when I'm conditionally valid on the prompt Pn+1, what it means is that the advertised level is kind of uncorrelated with every possible function of Pn+1. So what that means is that the miscoverage rate, or the error rate between the actual status and the target, has an inner product with f of P, which is 0. So for every possible test function, I should have a 0 inner product. That's what conditional validity means. When we turn to marginal validity, which is, of course, much easier to achieve, what that means is that if I think about it as above, it means that marginal validity is the same guarantee, except the function class, the correlation that need to be 0 are not just correlation with anything, but just correlation with essentially constant function. So it just says that the mean has to be okay. And so in between conditional validity and marginal validity, there is a whole range, a whole spectrum of approximate conditional validity. And so what that could be, it could be something like this. I could give you a function class, and what you might actually want is that the error rate be uncorrelated with f of P of n+1 when f belongs to a function class. So I don't want to be abstract in this lecture, but it could be, for example, that your function class is an indicator. It's a linear combination of group indicators. What type of prompts are we looking at? And if we restrict, for example, and maybe for the purpose of this talk, it's sufficient to think about f, the class script f, as linear combinations of group indicators, then when you achieve the conditional-ish validity statement that you see at the top, what this is saying is, if these are group indicators where, the indicators are G, are group G, then what obeying the top means that if the prompt falls into a certain category, then the probability of correctness is what you advertise. So this is saying that if, for example, my function class was a linear combination of group indicators, and this group might overlap. It might be the gender of the person. I want to write a biography about whether that person is dead or alive, and so on. These things overlap. But no matter what group you belong to, then I'm well calibrated. Okay, that's kind of what this is saying. So we're going to try to achieve that. And the way we can achieve that is by changing a bit what people do in conformal prediction. So essentially, we're going to calculate, there are two innovations in this way we're going to improve on conformal prediction. First, we're going to have an adaptive level at which we want to issue a claim. This is what we've seen before. And then we want to make it conditionally valid on attributes of the prompt. And so to calculate the threshold at which we should filter the claims for your test prompt, Pn+1, we're going to run essentially something that looks like quantile regression on the scores, on the conformity scores. And so we're going to find, we're going to look at all the G in the class script F, which is essentially the level at which we want to make the granularity at which we want to make conditional statements. And we're going to run a conformal quantile regression. So L alpha here is a famous pinball law that people use in quantile regression. You give me a prompt Pn plus 1. I'm going to solve this regression problem, and I'm going to hold a function g. And then the level, and so the data point S, the imputed conformity scores for the n plus 1 for the test point is not imputed yet. It's something that is in the optimization. And so we're going to look at the threshold T hat is the largest thing you could impute such that S is below the quantile function. So we're going to illustrate this in picture in a moment. At the moment, it looks a bit abstract, this procedure. The way how you can compute this is a topic in itself. We're going to discuss this. But we compute this threshold for your prompt Pn plus 1, and we're going to keep the claims above this threshold. And this threshold is prompt dependent. It depends on the prompt you gave me, and it depends on the level you want to achieve. And what we can guarantee is is that the thing I want to get? Yes, what we can guarantee is that this is going to offer you the validity you're looking for. So for example, if my class of functions is simply linear combinations of group variables, you have conditional validities over possibly overlapping groups. And so this is good. So this means that I can offer a calibrated assessment of the claim that the list of claims is correct, which is true no matter the group a prompt belongs to, and that's what this guarantees. And this is done using arguments of optimization theory and exchangeability, and I'm not going to give you too much details about the proofs of this fact. So this is giving us what we want, and I'm going to contrast this a bit with what the straight conformal prediction does and what these two computer scientists at Stanford had done. What they had done is that basically run the optimization problem we saw before, but with an alpha that was not prompt dependent, that was not adaptive, and a function class which was just constant. So if I actually simplify the problem considerably by saying the function class is just made of constant functions, and I'm not going to try to find an alpha that is adaptive, then we can look at the same threshold T hat, which is the largest S at S is less than theta S, but everybody would recognize that the theta that minimizes is a quantile of the SIs, and that's exactly what we've done before, is a tau hat split that we've seen before. And I think the limitation of thinking about it this way is that tau hat does not depend on the prompt, does not depend on the type of prompt you're looking at, and does not depend does not depend on Pn plus 1. And so just to contrast the two methods, and this picture is a bit cartoonish, but I hope that it will illustrate the main point, which is that each blue dot is a score S, and then you see this as a function of features of the prompt. And so what the original method we've seen is achieving, it's basically computing the quantiles of these scores. And so it returns a tau hat, which is the 90th percentile of this score. It doesn't matter where the prompt lands in feature space, you're always doing the same thing. On the right-hand side, you see our proposal. Our proposal is actually looking at prompts here. It partitions feature space into regions. And so it gives you a different level at which you should filter the claims depending on where you are in feature space. Okay, so now that we see that we're doing something adaptive, there's something a bit puzzling about all of this. It's funny that this is kind of things you can write quickly, but actually seeing whether this is computable is a completely different story. So how on earth would I actually compute this? So if we look at this, the threshold I should use for your test prompt is the largest score I could compute such that S is below the sort of regression function fitted using this S. So it seems a bit circular. And here it's kind of very nice to actually make the connection between quantile regression and linear programming. So I don't know if people know this, but the solution to the optimization problem. So let's think that my function f, g that I'm finding, my function g that I'm fitting is a linear combination of features of the prompt. So it's something that we're all familiar with. It's a linear combination. You know, I take my prompts, I featureize them. This is phi of p. And then the regression function is a linear combination of these features. Then I don't know if people know this, I'm sure they do, that the solution to this optimization problem, because the pinball loss is piecewise affine, is actually a linear program. And so you see here how you would actually implement this. You know, you would say, oh, I recognize an LP, and this is my LP. And now that we recognize this an LP, we can look at, okay, this is a linear program, so the dual of a linear program is also a linear program. And here it is. So I have the primal program, I have the dual linear program, which I see on the right-hand side, which has dual variables, which we call the eta i's. So I can think about my problem either in primal space or in dual space, so to speak. And solving one is equivalent to solving the other. But what turns out to be very interesting here is that by looking at the dual program, we're going to be able to actually find this threshold fairly efficiently. So why is that? So let's focus on the dual program, which is what will the system that Isaac and John have built is focusing on. We're going to see that eta, the dual variable, is a proxy for coverage or for probability of being correct in our example. So when I say, when is it that S is less than G of S at Pn plus 1? It's basically the same as asking that the dual variable be less than 1 minus alpha n plus 1. So for example, if your level is 10% or 90% of alpha n plus 1 is 0.1, saying that S is less than GSP, which is what you need to find the largest S so that this is true, it is formally the same as saying that the dual variable is less than 0.9. Now, the dual variable will depend on S because S is part of the dual program. And then this dual variable happens to be monotone in S. So using these two facts, we can have a fast algorithms for actually finding the threshold for an individual, for a test prompt. And it's going to go like this. Here is, we see, we have our test prompt. We impute the score S, and we say, is S less or G of S? So here you see the function G of S being fitted. And all I do is I could solve my linear program. I check the value of the dual variable is minus 0.1. So no, that's not, that you can raise S. S is not at the value that you need. And so we're going to raise S until the dual variable reaches 0.9. And so I have a little animation. We'll see how it works live on Zoom, but you know, I'm raising S. Now the dual variable jumped to 0.1 in increase. And you see that I raise S. Of course, the regression function is pulling it towards itself. The dual variable is still 0.1. I hope you can see my animation, 0.1, 0.1, 0.1, and so on. And now it's 0.9. And now we've reached the S, the last S at which S is less than G of S. And that's our threshold. So you can see that by basically tracing this path, we can calculate the threshold. And you'd say, well, I have to try every possible value of S. No, you don't need to do this because you can predict the joint points. And so maybe I'm going to skip this thing, but what I'm trying to convey with this graph is that basically trying to find the threshold is a matter of milliseconds. So using a modern computer, we can calculate thresholds for any test prompt in really matters of milliseconds. So this is a computational cost that is very, very low. All right, so we're doing this. So then we have our threshold and we can filter. Now we're going to talk about the two things that we've left out. One is, well, at which level should you make a claim? Should you make a claim for all prompts at the 90% level? We thought this is a bad idea because you're not going to be able to retain many claims. So at which level should you make a claim? So we mean that the goal is really to pick alpha pn plus 1 so that we retain 70% of the claim. And it would be a mistake, both statistically and for things that perhaps you understand from, it would be a mistake to just calculate this threshold based on the n plus 1 prompt alone. For conformal prediction, and here I'm just talking about people familiar with conformal prediction. For conformal prediction to work, somehow everything needs to be symmetric in the test point and the calibration point. So just looking at the test point to actually figure out at what level we should make a claim is not a good strategy and would actually lead to failure. That's akin to a selection bias in the standard literature in statistics. So the way we're going to do this is we're going to say, well, what we're going to do is we're going to run conditional calibration on a grid of level, like at every percentage point, 1%, 2%, 3%, and so on. Then for each prompt PI, we're going to define alpha I star to be the smallest alpha at which our objective is satisfied. 70% of the claims are preserved for all larger level. And then we're going to try to learn what, as a function of the features of the prompt, what predicts the level alpha I star, at which I should make a prediction. And so we're going to fit a function alpha to these pairs of 0.5 of pi alpha I star to create our function, which would take features of a prompt and return the level at which we should make a claim. And pictorially, this might look something like this. So we fit the method at fixed levels, and then we adaptively learn as a function of the features of the prompt at which level we should make claims. So here this plot is kind of interesting because the features of a prompt are the number of views a certain biography gets on Wikipedia, and we can see that the confidence at which one to make a claim or alpha decreases as a person becomes more and more popular, which makes sense intuitively. Okay, and then the last piece in the last 5-10 minutes is about boosting, which is that, perhaps engineers have several ways of scoring claims, and we would like to use powerful scores because we want to retain as many claims as possible. And so this is something that's going to sound very familiar to people. A lot of you are working on machine learning and boosting and so on. So what we want to do is perhaps the way I score my claims. Remember, a score, we can interpret it as sort of an a priori likelihood, an imperfect likelihood that a claim is correct. A high score means it's likely to be correct. A low score means it's likely to be incorrect. So I might have a probability model that depends on weights that essentially estimates the likelihood that a claim has of being correct. And so that's my score. It depends on some parameters, W. And then what I want to really do is maybe I would like to optimize the scores, W, such that the number of claims that survives the thresholding operation is maximized. So I would like to do a little bit of fine-tuning maybe on my scores so that I retain as many claims as possible. So suppose that maybe we have different scores. Maybe the chairman of this session has a score she has her favorite score to evaluate the likelihood that the claim is correct, but John has a different one, Isaac has a different one, and maybe some super expert at OpenAI has yet another one. One way we could combine the scores is by taking an sort of a weighted average of these scores to say how should we actually compute a super score, an ensemble score, if you will, that would maximize the probability of retention. So in that, this is a simplification of what we've seen before. What would I do is I would try to learn how should I score each individual score functions to maximize retention. All right. So what we're going to do is, well, these are theoretical expectation over populations I do not see. So the first thing we're going to do is we're going to replace this with an expectation over the data you gave me. And then because we want to optimize W, we're going to run something like gradient descent. We need things to be differentiable. And so, we had an indicator function, and we're going to make it soft by using a sigmoid approximation, because we want to be able to differentiate through to keep on moving W to maximize retention. Now, of course, the threshold that you're going to compute depends on the scores. So it depends on W implicitly, right? It depends on W, right? So if you change the score by changing W, then you change the threshold W. Okay. So this looks a bit daunting. So what we want to do at a high level here is we would like to be able to differentiate this through this stuff. And the question is, can we do it? Because tau hat is a solution to a quantile regression problem. So it's not exactly clear how I'm going to differentiate this with respect to W. How would I differentiate the first term with respect to W? I think it's completely clear. How I differentiate the second term with respect to W is absolutely not clear. But again, this is where knowing a little bit of optimization is helpful. So this is our quantile regression problem. Tau hat is a solution to this optimization problem. And so let's look at this through a picture. So here on the y-axis, on the x-axis, I have the featurized, I have the prompt in feature space. On the y-axis, I have the scores. Each dot is a score. And then I'm feeding this quantile regression function, which is what we see over here, at a particular point, Pn plus 1, which we see here. And then I see the computed score. This is what we've seen before. This is the first time the dual variable is equal to 0.9. So tau n plus 1 is basically the prediction at phi n plus 1. Now, because this is actually a linear program, it turns out that we can use a basic fact of linear programming, which is this, that this point is basically, there are exactly 4 points. If I fit a regression function in 4 dimensions, the exactly 4 points, which are the red scores that you see here, that completely determine the value of tau hat n plus 1. And these are, like, for those of you who do linear regression, this is where the linear programs, this is where actually the fit will exactly interpolate the data points. The fit will actually choose 4 data points at which it will exactly interpolate. The residual will be 0 here. And then the linear interpolant you get is actually what calculates tau n plus 1. So what that means is if I knew which data point is being interpolated, then I could calculate, by definition, the score tau n plus 1 is given by the prediction phi n plus 1 at beta hat, but beta hat is of this form because you get this by solving a system of equations. Okay, so this becomes quite friendly now, and because what's kind of remarkable about this view of the world, which John and Isaac have developed, is that as you change W ever so slightly, and this is what I'm doing, so I have again an animation to show you this. As you change W a little bit, you can see that the points that are being interpolated do not change. So I don't know if you see this, but they do not change. They're always the same 4 points. Which means that when I need to differentiate tau n plus 1 with respect to W, it's straightforward. I just need to differentiate the score, and the optimization problem is just simply a linear interpolation now. And so I just differentiate the linear interpolate, which is trivial. So it's basic linear algebra, right? And so this is showing that you're now changing the basis. It's called the basis in linear programming, and therefore differentiation is straightforward. So to actually boost the conformity scores, to, for example, learn what would be the best ensemble of scores to maximize claim retention, we can compute gradients fairly easily. So if we go back to the general formula, we're going to need to differentiate this, but that's trivial. We need to differentiate this, but we saw that we have a formula for doing this. The only thing we need to do is to differentiate the scores themselves with respect to W, which we're going to do by auto differentiation. And so at the end, you package this together. And what I'm going to show you is that when you actually do this, perhaps I'm a bit out of time, so maybe I'll skip this slide. And just to show you that as you actually go through these gradient steps, you're going to basically increase the percentage of claim that you retain. So we started with a bunch of scores, and now we're going to optimize the scoring mechanism. And so, what you see is that on the left, you see the new scores. So W is changing, so the scores are changing. And on the right, you see, as you go through sort of this boosting style iteration, you see the percentage of claim that you retain is going to increase as you find better scores. And so you get both the increase on the test split data set and then on something which is completely out of sample. And so you can see that, as we go through this gradient iteration, indeed, we see that we jump from something about a retention of about 30% to something like 50%. So at least in this example, then you start overfitting, so you should probably stop there. And so we can see that this boosting, at least in this example, can really help claim retention. Right? The scores have not been optimized for claim retention, and you can really try to find where you should actually be in score space to maximize retention. Okay, so this is working well. And so just to go back to a plot that we've seen before, so this is a plot showing that we're well calibrated, and we're well calibrated no matter the kind of medical questions you ask me. And so now we had not seen the blue. The blue was actually not using boosting. The orange is using boosting. And so you can see that as I move from no boosting to boosting, I really improve the retention rate. And perhaps you remember from earlier in the presentation that the lower bottom of this plot makes sure that we're correct 90% of the time. This is not adaptive, but it shows you the impact of boosting. So this has, when you actually put this together, you can ask ChatGPT, how often is a shingles vaccine required? This is what it actually outputs. If we look at the straight conformal method, it basically erases everything to make sure that 90% of the time what you read is actually correct. It will just say the shingles vaccine is typically recommended for adults, and then it would remove everything else. Our method will actually delete some of the claims. This is in red. You see the claims that are being deleted, and it will give you a correct calibration score as to what we think is a chance of what you're reading is actually true. Here it says 63%. And so again, when we say 63%, it means that we're about roughly here. And so 63% what we're telling you is actually true. And so it has a much higher retention rate. This is for biography. So for biographies, boosting is not really helpful. And the reason why it's not really helpful is that there is very little signal in the features to actually detect whether a claim is true or not. And so in this case, boosting is not really helpful. It is very helpful for the medical question, but not so much for the biographies, or at least maybe we're not using the right scores yet. So this is a topic for further research. Like it's very hard to extract signal in this application. So just to highlight the differences between what is in the literature and what our paper achieves, we asked ChatGPT to write a short biography of John Doyle. This is what it produces. If you use the method of Mori and Hashimoto, it just keeps joining. John Doyle is earning a reputation. I'm not exactly sure what you're supposed to do with this. And for us, it's going to say something we're pretty sure it's actually correct. And it's going to remove some stuff, but it's going to keep a lot of the claims, which in here again happen to be correct. So I'm at time, so I think it's time to wrap up. What we provide is we essentially leverage and improve conformal prediction to do hallucination removals with finite sample guarantees on the error rate that we advertise. We're trying to do our best to trade off utility, like please retain a lot of claims versus hallucination. I focused on the output of language models, but I don't know if you're like me. I live in a lot of different communities where more and more people are actually using AI systems to automate tasks. And we would like to score tasks, whether an AI system has done something correct. So for example, you might actually to filter toxic content produced by language models, or in a very different area, compliance. So you have a task, you would like an AI system to actually perform a task, and how do you know that what it has done is correct? And so these are tools to help you assess or calibrate the chance that what a system has automated is actually done correctly. I thank you for your attention. I hope that we have a few questions, and John and Isaac are on standby, ready to answer them. Thank you.